Hello everyone, this side Mrinal Jain. Sorry to keep you guys waiting. I welcome each and every developer today and a coder who is here to learn about machine learning. And After the exciting session of yesterday, I hope you guys must be waiting for today's session as well, because today we will be actually getting our hands dirty on the code and trying to predict the COVID mortality rate using the different methods which Shivang taught us. I can see a lot of introductions in the comment section. So yes, guys. Meanwhile, Shivang joins us. Just make sure you guys keep on sharing this video in your college groups, and various platforms, so that we can gather more and more audience, and we can start the webinar pretty soon. Just let me know in the comment sections, like from which part of the country are you joining, or from which college are you joining. So Shivang would be soon with us, and then we'll start with the webinar, because I don't want you guys to wait any further. Just start with your introductions in the comment section, and I'll just add Shivang to the feed then. Great, great. I can see a lot of people from Delhi and different colleges of Madhya Pradesh as well. A lot of people from Bangalore, a lot of people from Chennai as well. That's really great. Awesome, awesome. Just let me know if how many of you attended the yesterday's session and who is attending today's session as well. Just let me know who is users who are coming back. We have Shivang with us, and we'll be adding him to the feed within a minute, and we'll be starting the session. Great. Make sure for the questions. Yesterday also, due to a lot of comments and a lot of questions mixed up in between the comments, we were not able to take a lot of questions. Today, just make sure that last 15 to 20 minutes we'll be keeping for the questions. So if we miss taking your question, just make sure you ask those questions in the last 15-20 minutes. So don't be disheartened that your question was not answered. Just make sure that you ask it again in the last 15 minutes, so that we can take your questions. So that's what would be the flow of the webinar. For initial 50 minutes or 1 hour, we'll be talking about the practical implementation, and then last 15-20 minutes we'll be taking your questions, and then we'll be taking this based on your feedbacks. We'll be taking this webinar ahead and webinar series ahead, and we'll be bringing you more such topics in collaboration with TechEra community. They have been helping us a lot with the organization of the event, and reaching out to this various sets of audience from different parts of India. So yes, they have also played a very important role in this. So yeah, yes, guys, keep on sharing the webinar. We'll be adding Shivang in the feed in next 1 minute. Hey Shivang, how are you? Welcome.
Hi, Mrinal. I'm doing good. How are you?
Doing great, doing great.
Yeah.
Like just
Uh,
going through the feedbacks of yesterday's session, and like they're pretty awesome. A lot of people are
uh,
waiting. We already have close to 200 people like waiting for the session. So I guess if you want to sort of start with a small introduction, or anything which you want to say, and then we can directly jump into the webinar. And I guess
Definitely,
it's over to you. Yeah.
definitely. So thanks a lot, everybody. I just want to confirm my voice is audible to everyone. Uh,
Yes.
yes. So thanks a lot, everybody, for joining us. It's always great to talk about AI. We are in the very right time of getting into artificial intelligence. It's just 6-7 years now when AI has actually taken up the speed, and we are very within 10, 15 years, within 20 years, the world is completely going to change because of the new innovations which are coming up into the technology industry. So it's great thing, and more people, especially from Indore region and all other, more and more people get into AI, get into deep learning. This will greatly boost the companies who are working here into this domain. So not uh, not taking a lot of time about talking different things. Let's quickly jump and let's first of all uh, go for a quick recap of what we discussed tomorrow. I mean yesterday, and then we can quickly start working on our thing. So going back here, we discussed that we will be implementing CNN today, and we saw that CNN is nothing but a lot of convolution layers and a lot of pooling layers. And this CNN that starts from here to here is acting as a feature extractor. It tries to do the feature engineering for us. So just like we discussed, like in classical machine learning, people require to do the feature engineering by their hands. In our case, a deep learning model can do the feature engineering by itself. And then we also saw what exactly is the meaning of feature engineering. So if this was the data set a classical machine learning algorithm can fit, or we have to hand transform the things. So seeing this as a Cartesian coordinate, we'll have to write down a formula to convert the data set into a polar coordinate, and then we can put a linear classifier. But in case of deep learning can find out all kind of patterns by itself, and can get into a lot of stuffs. So that's what we discussed. Then we also saw what a convolution layer is, and how convolution layer is extracting the features. Then we also discussed about how activation functions are responsible for bringing the nonlinearity. And then we also discussed about uh, the pooling layers, how we are using pooling layers. We are basically using pooling layers to reduce the depth, reduce the size of the numbers that we have. So for example, if on this image, if we are implementing 10, if we have a 400 cross 400 image, that is 16,000 numbers. And if we are implementing 10 filters, so that will take the depth of 40 cross 40 cross 3 to, if you're implementing three size filters, so this, if you see that, this will be able to fit at 38 places. So that will take the size of the image to 38 cross 38 cross 10 depth. So number of pixels are a lot, number of features, number of that's like number of pixels are a lot, data points are a lot. So we want to reduce them down, and just to reduce them down, we implement pooling. It's just downsampling the image, so that at the end of the day, we can reach up to very few dense features which we think can be able to implement things. Then we also discussed about the last layers, and how we can implement cross entropy cost function, and we'll be implementing some activation called softmax at the end, which is going to give us a probability distribution, three numbers whose value will be between 0 to 1, and all three will sum up to 1, and the numbers will represent the probability of having a particular class, normality or pneumonia or COVID, into that image. Then we also discussed about how we can train the model. We can train the model using gradient descent class of algorithms, which basically tries to find the minima of the model, minima of the loss function. Then we saw that there are so many different algorithms which try to reach to the lowest of this. There are certain nitty gritties which I don't want to go right here. But if we see, all this is doing is it is trying to calculate some kind of a partial derivative. These theta, these are nothing but the weights right here. I think there is a abstraction into the view. These weights, not written here, I'm sorry. But basically, we discussed that to find a line, to find a model, we have to find two numbers, W and B. And in other cases, these numbers can be a lot. So these theta are nothing but uh, nothing but the weights, and then we are trying to do some kind of a partial derivative and subtract it down to that. The reason why we are going into it will incur some kind of a talk on uh, uh, Taylor series and some kind of talk on Taylor expansion of few things which we want to ignore for now. But basically, we are trying to move into the direction of gradients. The gradient is nothing but a big vector of partial derivatives. So that's why we are saying gradient descent. We calculate a lot of partial derivatives. We put it into the vector so that we can get some kind of a direction. So derivative is nothing but the slope of a curve, and when the curve is in 3 dimension or 4 dimension, to find the exact slope, the to find the direction of steepest descent, we'll have to have derivation, we'll have to have partial derivatives into all 3 4 areas. And as we all know that vectors can represent direction, so those things are known as gradient. And because we are reducing, we are making a descent, so that's why this algorithm is called gradient descent. So gradient descent is nothing but this simple rule at the end of the day. Although most modern algorithms do not use gradient descent, because at this given point of time, the partial derivative or the slope or the gradient will be zero. So if I start from here, I will not be able to reach here. I'll be stuck into this minima. So there are so many heuristics that have been developed to solve this problem, and those create a lot of things. The one that works best in most of the image processing problems is Adam. So that's what we did, and we also discussed something called back propagation and forward propagation. So this step, if we see, prediction and computing loss is basically a forward propagation in the neural network. When we give the image, uh, when we give image as an input, it do all these kind of operations, and at the end of the day it generates 3 numbers for probability. So this particular process of giving an input and generating the 3 numbers is called forward propagation. Now because in the process we are multiplying our image with a lot of random weights, that's why our answer is going to be random, and this will be very far from the actuality. So this will incur some kind of a error, some kind of a loss. So we calculate these loss with every image, and we sum it out, we average it down, and create some kind of a cost function. And the way to reduce that cost function uh, is to update the parameters. And the way we update the parameters is by using gradient descent. So this particular step we calculate all the gradients, and we implement this with every weight. So this is nothing but a partial derivative of uh, the loss with respect to that weight. So if weight is something, and if I try to change, uh, if I try to change this particular feature, this particular number, then what is going to be effect on the loss? So if I change some weight of this layer, what is the impact on the loss? If I change this weight, what is the impact on the loss? So if we see, that is what we are doing right here in gradient descent. And then with every layer, every convolution, every filter, every weight, we try to compute the loss, partial derivative of that loss with respect to that, and we subtract this out, and this huge computation we are doing step by step by step. Now, because this is a CNN is nothing but, or any neural network is nothing but chain of function. This is a function of an image. Because this is a chain of image, we have multiple layers, and everywhere we are doing some kind of a computation. That's why to compute all the weights, all the partial derivatives of the weights, partial derivative of the loss with respect to weights in this filter, partial derivatives of the loss with weights with respect to this filters, to computing all the partial derivatives in the most optimized or most efficient way, we have this step called back propagation. So the way we train our neural network is exactly the same. This thing, random initialization, predict, compute loss, and then update the weights. Uh, compute loss is forward propagation, and to update the weights we have to use gradient descent. But to apply gradient descent, we'll have to calculate partial derivatives, we'll have to calculate these gradients. To calculate these gradients of all the weights of this neural network, we implement another algorithm called back propagation. So that's what we do in entire thing, and then we keep on doing it. So this is what we are trying to achieve into the process. And let's quickly get into the code. And but before getting into the code, I would like to show you something cool. Let me take you to TensorFlow Playground, and let's have a quick visualization of what happens. So this is a problem. If you see, this is a simple problem, and we want to find out some kind of a symmetry to solve this problem. So there are two input, x and y. Let me reduce down this, and we have one layer here. Let me reduce down, and so we have one layer out here, and we want to do some kind of a classification. I'll put three neurons. For now, let's ignore the nitty gritty of all these things, but there's something called these neurons at this given point of time. You can for now consider as filters. uh, like if we go and not into the details of a lot of the things, it's going to take a lot of time. But for intuition, let's consider, although this is not a CNN, this is a feed forward neural network, but just let's consider that very 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 intuitive way, very crude way. Just consider that these are the filters of a CNN layer for now, although this is not a image problem, but let's consider that. And then instead of this, let me select uh, linear activation. Basically that means there is no activation. Let's not talk about regularization for now, and let's not talk about learning rates and all those things. And if I try to run this into the process, see what happens. See, it tries to do some kind of a suppression in the process, and it really finds difficult to do a lot of things. So let me stop this. Let me add another layer, and let's see what happens. Nothing effective at this given point of time too. Let me stop this again. Let me remove this layer, and let me put a sigmoid. Let me put a sigmoid, and let me also remove this layer. Let's only have one hidden layer with three neurons, three filters. This is the input layer, the image layer, this is the output layer, and this is the middle layer. Similarly, in our case, somewhere here we can say that this is the input layer, these are the hidden layers, and then this is the output layer. Hidden layers, we have two type of layers, a convolution layer and a pooling layer. So similarly, if we quickly jump, and if we put a single layer in between, and if we put some kind of activation called sigmoid, let's try to see what happens. Let me select some other data set so that there is a good visualization. Let me check and see what others we have. Let's try to run it over here. See, now in this case, it can quickly learn what goes. It can quickly create this decision boundary to separate these things. So even if I remove this and I put a linear classifier and I run this again, see, it very quickly can do a classification. See, I am not putting any kind of an activation, but see how easily it is able to do a linear classification over here. Instead of this, let's jump into this problem, and let's try to see what happens. It find a bit difficult to come to any kind of a reasonable logic. And if I put a relu here, and if I try to run this again, see, as I put a relu, it tries to reach, and it has automatically learned curvature, some kind of a circle. So everything below this circle can be classified as this. Everything above this circle can be classified as this. And if you see these lines represents nothing but the weights, the numbers. So as you see, the lines which are thicker having higher weights, the line which are thinner having the lower weight. Instead of this, if I would have put a sigmoid over here, let's see what happens with sigmoid, and I train it. something happens. I'm not sure. Let's wait for some time. It's taking a lot of time to get to some results. Maybe something is happening, some kind of options are happening. See, the loss is dropping down, and finally it has reached to some kind of a surface. If I change it back again to relu, see, within a second it reaches. But the same data problem, if I change it to sigmoid, it takes a lot of time to find the solution. See, if I put this to 10h, let's try to put this to 10h, and let's see what happens. Oh, it reaches to some extent. If I increase the number of layers, what happens? If I try to increase the number of layers and I put linear, I don't put anything, and let's try to solve it with a bigger network. See, it's getting very difficult for a neural network to find the symmetry. It's almost not possible. Almost no, it is not possible for a neural network to find this curve because we are not putting some activation. Let me stop this. Let me put relu again. You see, this time it took some extra time to get to the curvature. The reason being the network was big, so there were more weights. And as we already discussed, we have to compute a lot of partial derivatives. So as we compute a lot of partial derivatives, now there are more filters, more layers. It takes some more time. Now, if instead of this, if I put a sigmoid here, if I change this and I put a sigmoid here, we think that it will converge, but it's going to take a really long time to converge. And now filters are very less, but when we are talking about big CNNs, when we are talking about images, when the image density, image pixels are like 1000 cross 1000, it is really difficult to converge from sigmoids. So sigmoid, they all bring non-linearity. It's a great question why these functions enable a network to learn any kind of a symmetry, but with the problem with sigmoids are it is difficult to compute. It takes some extra time to compute their partial derivatives because of the formula. If you jump, let's put it right here, and let's jump here, and let's somewhere down the line we must be having a formula for sigmoid. Let me see, do we have somewhere? Oops, just give me a second. I think it should be somewhere. Yes. So if you see, the formula for sigmoid is 1 upon 1 plus e to the power minus x. So it includes some kind of an exponent. And to compute this, you require, this is a bit complicated to compute. It's not that fast. And in case of relu, relu is very straightforward. I think we must be having relu somewhere here. Relu is straightforward. It is 0 or it is that value. So calculating the partial derivatives is quick. Either it is 1 or it is 0. So because of this, this is a 45-degree line in most of the cases, and this is 0. So for negative values, we give it to 0. For positive values, we leave it as it is. So if you see, that's why most of, even it takes some time to converge. It couldn't even converge till now. So because of this, most CNNs use ReLU. But if you put sigmoid, it also works, but a bit difficult. So let's quickly jump to the code, and let's see what happens. So we have created a simple version of the entire problem for you. So this notebooks works on currently it is deployed on in AWS T2 large server. Because this is T2, this is not a Pascal architecture. It will take a lot of time for us to train it. But what we are doing right here, we are importing TensorFlow STF. So TensorFlow is a library that is doing all these linear algebra calculations for us. So Tensor is nothing but metrics basically, and then we are building Keras, a high-level API, which makes really easy for us to implement models. Then we are importing layers, and there we are importing models. So models we can import MLP, like normal neural network models. We can import a sequential model, basically that can be a CNN, a convolutional neural network. We can also import recurrent and all those things. And we are also importing layers. So with layers we can import a convolution layer. With layers we can import pooling layers, flattened layers, and all kind of recurrent layers, all kind of things. We're also importing NumPy, and we're importing matplotlib to plot things. Now, as we see, a lot of these things involve some kind of a calculation, calculating partial derivatives and doing a lot of stuff. All these things require, or all these things can be done very quickly with some linear algebra concepts. So NumPy and TensorFlow and all these are nothing but linear algebra libraries. TensorFlow is a linear algebra library which can run on the GPUs, and then NumPy is a linear algebra library which cannot run, like which cannot do higher performance on a GPU. So that's why we don't use NumPy a lot to do deep backpropagation or deep neural network training kind of stuff. If you come here, this is nothing but some kind of pre-processing that we are doing. We have imported, we have just certain, we have just mentioned what is the training file. So let's see this training file. This training file is train codext.txt. So let's see what this means, because training files should be an image. So if you see, this file contains a lot of image names. So these are a lot of image names that we are having. And then with that, it tells whether it is normal or whether there is pneumonia, whether there is COVID, or there is something else. This is nothing but the source from where we took the dataset. So we can ignore these things for now. But technically, this is containing some kind of mapping where it tells that this is the name of the image, this is the path of the image, and if there is a COVID, we have written it right there. There is COVID, there is no COVID. So this is one way we can maintain dataset. We can do it using a CSV file. We can actually store this in terms of a big SQL database if the database is very long. But uh, if you see, this is the X, not exactly, but this is something that can help us get the X, get the input. Exact X is the numbers, exact X is the numbers of the pixel. But technically, with the name of the image, we can go there. And this is the output. This is the output that we want, normal. In other case, this is the output. The output that we want is pneumonia. In some other case, the output is COVID. So we have some kind of a labeled data set. We are not only giving simple data set, but we are also giving a model the final output. So if for this image, if our model says pneumonia, then we say that no, you have done a mistake, it was normal. For some another image, if it says this particular image is having COVID, we'll say no, you are wrong, this is pneumonia. For this image, if it says this is COVID, we'll say yes, you have done a good job. So by this labels, by the actual ground reality, we can calculate error. For how many cases our output was right, for how many cases our output was wrong. Now, how can we calculate these error? There can be a lot of formula. You can simply count the number of errors. You can simply do some kind of a distancing. You can implement any kind of a formula. We implement something called cross entropy in this case. So as we discussed in our last scenario, we somewhere here discussed that we'll be using cross entropy loss. Why we are using cross entropy is it itself is a 3-hour discussion. Why cross entropy is required for a multi-class classification problem. So for now, for this session, let's ignore that. We were somewhere in the same thing. Now, similarly, we have a test file. So what we are doing, we are having a training file, and what we are having a test file. So we have made some kind of separation. We'll be training our model on some images, and we'll be testing our model on some images, and then we'll be trying to calculate the ground reality on the test images. The reason being, we are trying to learn the distribution, and sometime there can be sample biases. For example, there can be some kind of a pattern into the training dataset because of which it works really good in training datasets, but it failed to work on test datasets. It again involves some kind of stats, but right now we can understand that if I am trying to learn trigonometry, the questions that I've already solved, I know the answers. So if in the exam the same exact question comes, I could have remembered the questions and get good marks. But if I am unable to answer another questions which includes same concept, that means I haven't understood the subject well. I have just learned some kind of concepts. The same thing applies. Not this is just an analogy. The exact answer is sampling biases, because of which we are trying to do this. But technically, we don't want to generate the results on the data over which we have trained. So this is the data direct the dir that we have matched. Then we are setting a batch size. We are saying that every time we are taking 20 images. Now, what is a batch size? So if you remember, we are calculating gradients. So if you come back here, if you see, this loss is some kind of a summation. Everywhere you see softmax is some kind of a summation. Cross entropy, so this is some kind of a summation. So this summation is nothing but uh, computation of loss. So in our network, somewhere here, in our network, we are generating these loss for 20 images, and then we will be summing up and taking the average of loss for 20 images. So we have already discussed that to actually update, to actually update these things, we'll have to implement gradient descent. And to do the gradient descent calculation, we'll have to use back propagation to calculate all the gradients. So if we put in a million images into one batch and give it, there are two big problems. One is computer do not have that much memory to store or to do that level of a computation. And another reason is the loss function at certain places can be flat. So if we come here, uh, let's suppose actually our loss function will be more of this nature, even very high dimension. But let's suppose I am sitting somewhere here by chance. When I did a random initialization, I initialized this to this position, some kind of a plane, or on this I initialize this to some kind of a plane. Now because I am on some kind of a plane, my gradients are going to be very low. And because on a plane surface at the tabletop there is no slope. Now, and if there is no slope, I have initialized my weights up to this. So if I calculate gradient for one image, or if I calculate gradient for 1 million image, there is no point because everything is going to be summed to zero. So when I'm implementing gradient descent, when I'm subtracting my weights to the partial derivatives, I'm trying to subtract very small number. So that's why there is no point adding up 1 million zeros and then subtracting it. That's why we just want to compute 20 zeros and that's subtracted. So these are the two major reasons why we are implementing a batch. So this basically becomes batch gradient descent, where we are implementing some kind of a batch. Then we are saying COVID percentage. So this 20% of the images that we are taking, we are saying that I mean this 20 images that we are taking, we are saying that at least 30% of them must contain a COVID image. So because we are randomly sampling out 20 images, we this is something that we have written in the code. These are just variables I'm trying to explain, but we are mentioning that 30% we will be going to take from the random sample should contain. So at least 6 images should be of COVID. How we are doing, how exactly we are implementing is something that we can ignore for now, or we can see in few minutes. Then we are having a top percentage. This top percentage we are using to crop the images. So we want to crop certain and do some kind of a pre-processing, because there may be chances that the entire image there is some background or some other thing that also includes some kind of pixels, and we want to percent that out and get something to here. Then we are having COVID weight. So COVID weight is basically COVID weight is 4. That basically means that if we do a mistake in COVID class, we'll add the loss 4 times. So for any other, if we are saying the law, if for any other place, if our model makes a mistake, we consider a loss to be 10 units. So in case if our model makes a mistake we'll put the loss to be 40 units. So the error if I do to this particular class, it's just like if you fail in one subject is contributing more to your percentage, or one subject is computing more towards your error. So that's why we are making ourselves a bit biased toward the COVID class. We can all these are parameters we can work around and do certain things. And I'm just trying to give you some kind of a intuition of how we are thinking, how we are planning and working around. Then one class that we have implemented, balance COVID dataset. Basically, this is for pre-processing. So let me. Uh, so where is this? This is in data.python. So there must be some data.py. There must be some data.py somewhere here down the line. Yeah. So you see this data.py is having a lot of things. It has dir, it has csv file. Then this class has if training is equals to batch size. We have defined it. We have overwritten it there. So we are saying that every image is going to be 224.224. If nothing is provided, this is something that we are going to take. We are saying that there will be three output classes and channels. We are saying that the image will be of three colors. Then we have simply at the end of the day, we our model cannot say whether this is normal or pneumonia or COVID. It will just output some kind of a class number. So we implemented one dictionary where we are labeling that COVID means two, pneumonia means one, things like this. We will be shuffling. We'll be implementing augmentation. So augmentation is one way of increasing the data. So basically, if you have an image, if you turn it around, it's again an image. If you change the pixel, you flip it, that's also, if you have an X-ray image, if you flip it, it is also an X-ray image. So we are doing some kind of image augmentation to increase things. So the image augmentation class itself is something that we'll have to talk about half an hour to understand it completely. So I just want to move away from it. So here we have defined the class weights. If you see 1, 1, and 6, there we have updated it to some other number, but this is basically saying that we are, if nothing is provided, we are going to increase the impact the loss by 6 times for COVID, and other losses we'll consider it. Then all other things we're mentioning some data directors, and then we're mentioning the trainings and all different stuffs. We have certain functions that we have implemented. For example, next, this is going to take the next batch. So we are saying 20 times. We're taking one epoch. We are taking 20 images. So we'll take a random sample of 20 images. We pass it to our CNN. We take 20 images and then we pass it to our CNN. We compute the loss. We compute the gradients. We compute the gradients using backpropagation. We update the weights using gradient descent. So that is one epoch. Then we will take next batch, and the next batch we'll again take 20 images. Then we'll do a forward pass. In our forward pass, we'll be doing loss computation. Then we'll be doing a back propagation. In back propagation, we'll be computing the gradients. Then we'll be updating the gradients using gradient descent or adam or some other optimizer. And then we will update. So that will be our second epoch. Then it will be our third epoch. So we can repeat this process for 10 times, 20 times, 50 times, or we can repeat this process till our loss falls. If it stops falling or it suddenly increases, we can do some kind of a stop. So that batch selection, taking batch again and again and again, is basically done by this function we have implemented somewhere here. Then length, then on epoch end, what you are going to do on epoch end. So right now we are simply shuffling the data set so that we do not have some kind of a repetition. So here, if you see in our data set, if we take 20 images up front, so we are saying that every image is normal. So it is difficult for a network to predict the output, because in these 20 images, the entropy of the batch will be less. Everything is, entropy is nothing but variation. So in cross entropy sometimes comes with, basically comes from the concept of entropy itself. Let's move ahead. Then get items we actually are not using into this program for now. So let's ignore it. So that's what we have done. We have simply mentioned a lot of things right here, and instead of class weight to 6, we have updated this as 4 right here. And then this is what we have mentioned into the entire thing. Now we have calculated a batch x, batch y, and weights is for next. So weights we are basically taking. So every epoch we are updating the weights. At the end of every epoch, like we are doing one gradient descent update. So whenever we are doing one gradient descent update, we are computing some kind of an image. We can do this for every image too. We can actually implement the gradients or the weights with every image, but that also comes with some kind of an issue. In that case, our weights will be a lot so stochastic, a lot random, and then the loss will not be some kind of smooth, but there will be a huge variation. It will go crazy. So that's why we use batches to do some kind of small mini batches. So we have created this X as the input. These basically contains images, Y as the output, weights basically the weights, and we have implemented the same function. And at the end of the day, this batch X is going to be a big matrix. So if you imagine every image is, let's suppose, having 224 cross 224 cross 3. Every image is having 224 cross 224 cross 3 size, but now we are having 20 images. So we'll be having a 4-dimension vector, size 224 cross 224 cross 3 cross 20. So that 4-dimension vector is going to create a tensor. We call it a tensor. So here, this batch X, basically the train image is a tensor, and label are also again a tensor. So we got our X and Y. We This mapping is basically to set the output. The class name is this, so we know whether we need to pass 0, 1, or 2. And if we ignore all these things, so if you see, this is one image that we are trying to show. We have used matplotlib to plot this image, and similarly we have thousands of images with us. See, this particular server is a T2 large server. We just put it everything over here so that it's a bit less, it's a bit cheap. We put things on a P2 large server to train things. So that's why if I try to run this, the server is going to stop in the training process. So we have computed a lot of things in hand, and I'm just trying to go through it for you guys. But like, you require a GPU. A GPU is going to cost you ranging from $1 per hour to $15 per hour. So whenever we train a network on a real data set, we try to train it on a GPU. But when the network is trained, when we are doing some kind of inferencing, we can put things on a smaller server, so we can build a service. Because when you are running a software, then in that point of time you just want your network to serve. So serving can be done on a smaller network. So that's why, otherwise, if you are creating a technology and you are building a mobile application, where or you are building some kind of a IoT device where X-rays are directly connected to your servers. So send X-ray image to a server and it will give you back the results. So you don't want your server to cost you $15 per hour, because you might require 200 servers to process a million, not 200 servers, but yeah, good number of servers to process millions and millions of images. So you train and then you put it on a smaller server so that inferencing can be done. Because training is another part. Training is when you are doing these updates, where you are computing these gradients, where you are implementing back propagation and in gradient descent. And predicting is, or inferencing is, nothing but one single forward pass. Whatever the results you are getting, you are assuming that this is the correct result. So we have imported. So if you come up here, we have imported Keras, and Keras we have imported layers and models. So see, this is what we are doing. We have mentioned one variable, and we are saying that this must be sequential. So if you come here, we see that this is a sequential model. A MLP, or if you see CNN is a sequential model, there are some other models which are recurrent, which are not sequential. Though those we can ignore for now. So if you see, we have implemented a 2D convolution. We have added a layer. We have implemented a 2D convolution, At this given point of time, we are implementing our image shape is 480 cross 480 cross 3. We have implemented an activation called relu, and this is the size of kernel. We have implemented 3 cross 3 kernels, and we have kernels means filters. So we have implemented 3 cross 3 filters, and we are going to implement 480 filters. So on the first layer, we are going to calculate 480 low level features. So if we come here, right here, this is the image, and on this image, if you see, on this image, this is the filter. So if we implement this filter, we are going to get some output. So once we implement this output, the depth of this is also going to be 3, because this is 3. So we do a element wise multiplication. So our filter depth is 3 right now. So our image depth is 3. So we do a element wise multiplication all across the depth, and we create one smaller matrix, one smaller feature map. Then if we do the same thing with another filter, we get another feature map, which we stack it behind the scene. Then we stack it behind the scene, and we stack it behind the scene, and that creates a bulk. Over that bulk, we implement relu, and that is the output of our first convolution layer. So uh, in our case, if we come here, in our case, we are implementing 3 cross 3 cross 3. We don't have to mention depth, and we are implementing 480 filters over our image. So that basically means that our output dimension is going to be 478 cross 478 cross 480. So if you see right here, so if this particular thing is having a size of 7, so if my image size is 7, then I can put my filter at 6 unique places to do some kind of a convolution operation. So yes, for a 3, I mean, if my 5 places where I can put it there, n minus 2 places where I can put my filter. So if my image size is 3, my filter size is 3, then there is only one position. If my image size is 4, my filter size is 4, then I can place it to 2 positions, just as we see right here. Our input is 5, and then we have 3 places to put our filter. And if we see our output filter, which is coming the size 5 cross 5. So this is what we are doing right here. If we jump, then we are implementing a max pole 2D. That basically means that we are implementing a 2D channel. We come here, and we discussed we are implementing a 2D max pooling right here. So that even down samples, and there is no activation, there is no weights involved into the pooling layer. It is just down sampling. There is no weight multiplication. In this, we are multiplying the input with some weights. So here we are implementing some kind of a non-linearity. Otherwise, if we just multiply the weights, then this will create something like W1P1 into W2P2 into W3P3 into W4P4. That's basically a linear combination of the input, and that cannot be non-linear. So that linear combination, we implement some kind of a non-linear function. At this given point of time, we're implementing relu in the convolution layer because this is fast. It is fast for us to compute the gradients, as we have already discussed. Similarly, we again implemented another con2D. This time we implemented 64 layers. We again implemented relu. Again, we implemented max pooling. Then we again implemented a con2D, filters 3 cross 3 activation. So this is something that we can always plan. If we see an architecture of some other network within a minute, let's see it out. Let's see LeanNet 5, LeanNet 5 architecture. So see, let me increase the size. So see here in our image, they are implementing different number of filters, and every filter is going to have a different kind of size. We can ignore these numbers, doesn't matter. But there are so many different kind of CNNs that people have worked upon. There is LeanNet, there is ResNet is a bit different, but technically they all are having some different filters, some different layers, and then we flatten it out. So this is one image, and this image, we have a rectangle, so we flatten it out into one single number, one single vector. So for example, if we flatten this image, we are going to have a vector with, we are going to have a list if you understand a vector with 25 numbers. If I'm going to flatten down this, then this is going to be a vector, or this is going to be a list, not exactly a list, but from the conceptual perspective of 9 numbers. So that's what is happening right here. We are flattening this down to last layer with 10, 15, 20 things. So we flatten this out, and basically these are the final features that we want to learn. These are the final features that we want to learn in our case. Now at the top of these features, we implement, just give me a second. At the top of these features, we flatten this out, and then we implement a dense layer. Then the dense layer, this is going to be our last layer for for our output. So in our output, we just need 3 layers in that case. So this is, if you see, a summary of our model. In initial layers, in initial convolution layers, we are having 13,440 parameters. In our pooling layer, there is no parameters, as we already discussed. In our second layer, if you see, we have almost 200,000 to 2,76,000 weights. So there's so many weights that, see, if we see the total parameters, total learnable parameters are this many. How much? 1,100,000 lakhs, like almost like 5 crore, 54 lakh number of weights that this model have to learn to do something good. This is big numbers that our model has to learn, and these right numbers once defined. So these numbers, when the right numbers when defined, we reach to the right position in our loss functions. So if you see, this is just representation, because in our case, if we have 5 crore parameters, then our loss function is represented in 5 crore dimensions. So right now, because if you have 2 weights, then z-axis you will put your weight, x-axis you will put your z-axis you put your loss, x-axis you put your one weight, y-axis you put your second weight, and then you try to create some kind of a surface. But if you have 100,000 parameters, then your loss function is, we just can't imagine that, but it's going to be a very irregular kind of a high dimension surface. And on that high dimension surface, we want to find out some kind of a point where we converge here, where we reach to a loss, loss where our loss is minimum. That basically means we are very close to the output. So if we try to see, when we try to converge, so initially the loss is high because the prediction is very different from the ground reality. But over the period of time, as our line fits into the data, the loss reduces, the error reduces, and we want to find a way where it reduces. It do not move out, because if it move out again, the error is going to be increased. So that's what we are trying to achieve. Now, how we are training, how we are actually training our model. See, we have implemented an optimizer called Adam. So this optimizer is nothing but some kind of a gradient descent variation. There are Adams. There are even modern versions of Adams that people are using now. There are momentum-based algorithms. There's something called a Nextro accelerated gradient descent. There's something called an RMS prop. Adam is nothing but a combination of momentum and RMS prop to be very effective. So most of the current level deep learning, current level computer vision, Adam works. So it's like by default choice. If you want to train a CNN, you can directly put optimizer is equals to Adam, and that's going to work in most of the cases. Then we have implemented cross entropy. Sparse cross entropy is a type of cross entropy, basically, where we are trying to calculate the loss. So basically, the loss is some kind of a function of prediction and output. We can compute the number of mistakes the model has done. So in 50 images, if our model was 5 times wrong, we can say the loss is 5. Very crude terms. But then training model is difficult. There are so many reasons. There's so many reasons to implement. There are so many conditions to implement Adam or gradient descent or something like this. For example, our function should not be a step function. Our function should be should be having a regular curvature. So that's why we don't count mistakes. By that, for example, if this is a classification line, and if I slightly move this line, and there may be a chance that I'm still doing the same mistake. For example, if this surface you see, all the blue points lie here, all the red points lie here, and let's suppose there is some kind of a mistake. It fails to classify 20 numbers. So if I say the error is 20, I slightly move my surface, it is still 20. So that basically means that my loss is not a state function. I do some kind of change in weight, but there is no change in the loss. But at certain points, if I do some changes, the loss decreases a lot. So it's some kind of a step function. In those cases, it's difficult for us to train the models using gradient descent. So that's why we cannot use, and there are some researches done by the people to come up with some kind of a sophisticated algorithms, so sophisticated formulas to train our model. So there, some kind of a mathematical constraints lies behind, but all they are trying to capture is how wrong our model is. We can always go and we can always try to see what works at what point. But the point is, you are saying that your error is cross entropy. You are technically implementing a backprop, and here you are saying that your error is cross entropy. You don't have to do it step by step. You don't have to write these formulas and try to. You don't have to build this entire logic of forward pass and back propagation, and you don't have to do all these computations by hand. You don't have to do all these things by hand. That's what basically I mean to say. And see, to train the model, we simply are running this thing for 10 epochs. We are saying that our model is going to run for 10 times. There will be 10 forward passes, back passes, and there will be 10 updates into the weights. And then we are passing training images and training labels. And if we run this, this is going to initiate the training. If I run this, my error is going to, my system is going to hang because this is a small server and we have a relatively larger data set. Then to evaluate, we again have very simple functions. We can evaluate our model directly by passing certain things, and we are saying that the point of evaluation is going to be accuracy. So the point of evaluation can be MSE. That's another formula. Accuracy is nothing but percentage accuracy. So in 100 images, my model was correct 70% of time. I say my model accuracy is 70%. So accuracy we are doing this way, but computation of loss. So we are not saying if my model's accuracy is 70%, I'm not saying the loss is 30%. I'm using some other formula for certain reasons. But all we are trying to capture is mistakes. So this is basically what we are doing, and we can save these weights, the weights that we have captured. We can save these weights into some kind of file, and then we can load it later stage, and then we can simply do model.predict. We can pass some test images. It tries to generate the output for us. So this is basically it in terms of what we do in machine learning and how we train things. But the beauty of this thing, if you see, this is all you did. This is all you did. You implement 1 2 3 convolution layers. We implement 1 2 max cool layers. We flatten it out. We put a dense layer. We put certain activations. We put some output. And if you see, this is all we are doing to build this. And then if you see right here, if you see this, I scroll down, and if you see this model.compile and model.fit, these two line of code where we are mentioning Adam, that basically means that we are talking about everything that we discussed in this slide. This entire rule of computing all the gradients and updating this, but we are doing some other stuffs which make sure that we do not converge to a local minima and all those things. All those mathematical concepts are taken by us by saying that our loss is Adam. We're mentioning that our entropy is going to be cross entropy, and in that case, we are doing all these stuff and mentioning all the cross entropy for us. So, and then if you see, when we say model.fit, so that model.fit is going to take our model and run it for 10 epochs. So that's basically it. When we jump here we are doing in our CNN, we jump here, we implement a convolution layer, we implement multiple filters, we implement multiple pooling, then we run, and then we calculate some loss, and then we implemented a backpropagation where implement some kind of a chain rule to compute all kind of gradients, and then we implement Adam to update the gradients one epoch, and then we do this 10 times. The entire jargon that we discuss, which is difficult to do all implement all chain rules and understand things for the beginner, it's so easy to build a CNN and can do classification for COVID and all different things. So for a start, this is a great way of moving ahead. For a start, if we can understand things on conceptual basis, quickly implement and see the results, that's great. Over the period of time, there is so much concept, there is so much content that you can read day by day, and from an incremental way, you can understand it better. What type of activation functions are there, and you can study in much more detail why we require activation functions and what are the more sciences behind activation functions. You can get into and you can read a lot about gradient descents, so you can see what gradient descents are, the descent algorithms are, and what are the concepts behind it, how you can derive it, how you can find out perfect sense using Taylor expansion of certain things, how you see that momentum and Adam and most of the modern optimizers are working. You can work into it, and you can see read a lot of CNN architectures. You can see, okay, what are LeanIt, what are MobileNet, what are ResNet, what are different concepts, what are new researches which are going on. You can move and study a lot about backpropagation, how you can implement backpropagation from hand. So how to do some kind of a vector calculus and try to see things going on behind the scene. You can study a lot more about data pre-processing, data visualization, and how you are doing data augmentation, what kind of augmentation can be done at different places. You can see how you can take this model and convert it into a TF Lite and put it into a mobile phone, put it with your Django project, and you build some kind of an end-to-end API to do certain things. So one small thing that we try to deliver today is to expose you to the nitty-gritty, and we try to tell you guys that this is the way you can quickly get into deep learning. You quickly go and do some kind of an experiment and say, let's build something. There are so many tutorials out there which you can use to work upon, and day by day, when you are doing this, you will be a lot more curious, and with those curiosity, you can take topics and you can do research, you can study about it, and you can get into a lot of mathematics of it, you can get into a lot of implementation level knowledge of it, and you will see that over the period of time, you understand a lot of deep learning, you understand a lot of machine learning into the practice. So I would conclude my talk on this point, and I take it to Mrinal from now. Mrinal, over to you.
Yes, Shivang. Thanks a lot. Hope everyone might have enjoyed the session. So for like next few minutes, we are open for questions. If you guys have any questions, you can let us know. If you might have asked any questions in the comment sections above, just make sure you rephrase it again and mention it again. Ask it again so that it would be visible to us. Uh, so yes. Just shoot your questions if there are any.
I read a lot of comments saying that the font size was very small. I was actually sharing my screen, so I couldn't go through those. So, Mrinal,
So
if you want, I can reshare my screen, increase the font size, and quickly go through the code.
there were few people who were saying
Okay,
that.
then we can ignore it. Yeah, we will share everything to them so that they
Yeah,
can.
we'll be sharing it. And I asked, so there were like two, three people who were
Yes.
saying. So
Okay.
yeah, so we have questions now. So there's a question from Shivam. How should I choose the architecture so that I can get maximum accuracy?
So there are certain architectures. It's difficult to choose an architecture, and it is done by a lot of trial and error. So there are certain research papers that are implemented and done some researches past the scene. So simply go to Google and see what are the best CNN architectures out there, and the networks which are already created can be used, and they give this best results in most of the scenarios. So this work has been done by a lot of data scientists. So you can choose a lot of predefined architectures. You can go with LXNet, you can go with MobileNet, you can go with RISNet and all, and then it depends on the computation. So if you want to run your model on a smaller computation, then you can come up with a small network. If you don't have that problem, if your problem is really difficult, you can go with a network with maybe 150 layers. You can go with RISNet 150, but that will be big. If you have small data sets, you can take a small network. If you have big data set, you can go with that. You can also do experiments. You can come up with some kind of a network, you train it, and then you change the layers and see what results are. So it is experiment, it is statistics. Another way is neural architecture search. This is a type of reinforcement learning where we use some other techniques to train a network to find its own architecture. But those are something that is beyond the scope of this presentation for now.
Next question. It's from Tanush. From a beginner, what are the ways we can start our own data analysis project? Any website or any course which you would like to suggest?
Just go to Google and say 10 data science projects that a beginner can do. You get the link and you follow the tutorials. You go to YouTube and you go to Quora and say what are the best things. This is subject that you should do by working. It's okay if you don't understand everything, but if you implement certain things, you will be much more interested to do it. And then a lot of concepts are there. If you simply go to Google and say top 5 projects that a data science beginner should do, you can go home and implement an MNIST for digit recognition. That's the easiest thing to do.
Next question is which is better, GCP or AWS to train and deploy a deep learning model?
Both are good. Both are good. It depends on your choice, but both are good. It depends on customer's choice and where it is economical for them. But both are good. There's no, we can't compare apple to oranges. No? They both are fine.
Okay. Yeah, guys, keep on asking your questions. If you might have asked the questions at the beginning of the session or in between of the session, we might have missed your question over there. So just make sure that you ask the questions again over here. There's another question from a Facebook viewer that what is the difference between convolution layer and pooling one?
So pooling convolution layer is basically which is the layer where we are implementing some weights and we are learning some features. So the machine learning is happening on convolution layers. But to make sure that the network size is reduced over the period of time, to downsample the image, we implement pooling layers. So pooling is basically reducing the size of a convolution layer. So if you have 100 cross 100, we try to reduce it to 50 by 50 of some smaller size so that we can train and generate results effectively. So convolution is basically where learning is happening, where we are implementing some weights and implementing non-linearity. Pooling is just for downsampling, reducing the size.
Okay. It's not a question, just a request. Like, can you tell something more about annotated data?
Annotated data, there are different type of problems where different type of annotations needs to be done. If you are dealing with a classification problem, then you have to mention, you have to write down the name of the class. That is some type of a structured data you have to mention. If you are going for object detection problem, then you will have to draw a bounding box and you have to save the coordinates in the class of that image. So you want to find out whether where is the person standing, so you have to do that. If you're doing a segmentation problem, then you might have to segment out each and every pixel into the X-ray image to find out this is the corona area where it is highlighted. If you are dealing with NLP or some other problem, the labeling concept differs. So there are certain tools, and it depends from problem to problem, if I understand your question correctly.
Okay. Next question. What are the methods for image data cleaning?
uh, what are the methods for image data cleaning? What do you mean by methods? Features, functions, or how you do data? What are the concepts of image data cleaning? If you can rephrase this.
Mm,
Methods, if you see methods, by methods you have Keras, TensorFlow, and OpenCV as three methods to do any kind of image processing that you want. Uh, so those three libraries are having all the features, especially OpenCV, and then you can convert it into NumPy, and then you can implement any NumPy feature over here to do any kind of pre-processing. So these three, four libraries are good methods to do image pre-processing.
so yeah, I
And
guess.
yes, and if you say what if you ask what exactly means by image processing, that basically in most of the cases is taking normalization. So our pixel values stays from 0 to 255. We want to normalize it down to 0 to 1. We can get it into grayscale. So that if we want to, if we think that color is not important, if you are doing a dog and cat classification, and if you think that that can even be done with a grayscale image, so that can be pre-processing. It can be some kind of cropping. Then you can implement some kind of other image processing techniques to sharpen it out and all. But most of the times it is converting to grayscale, normalizing the image to in between, like scaling, feature scaling, and sampling it down, reducing the size of the image to uh, a certain size, so that a network can train it. We don't even train the network from scratch. There are so many weights out there. We take the weights from ImageNet competition, and then we fine tune our model on those ImageNet weights. Because in ImageNet competition, people train their networks on millions and millions of images. So those weights are really good to fine tune, to do some kind of a transfer learning on our own small problem set. If we try to train our model from scratch, if we actually do a random initialization and then we train it, then it takes a lot of time, or we require a really big computer, a really big group of computers to get the results. So this is what we do for pre-processing.
There's a question from Vivek Tiwari. How to avoid overfitting?
There are multiple ways of avoiding overfitting, depends on problem to problem. Uh, for those who are new, overfitting is a concept where your model is a problem, where your model works great on training and do not work that good on test images. In one way of avoiding overfitting is increasing the size of dataset. If you have really high dataset, really large dataset, you can work around. Another way of reducing is implementing regularization. So regularization can be of multiple types. So you can implement some kind of uh, additional features into your loss function, components to a loss function as some kind of a regularizer. And in deep learning, there are different type of regularization techniques. uh, for example, dropout is there, and we can even reduce the size of a network, because larger the network, more prone it is to overfit. So these are few, and there are many more. There is something called batch normalization, another way to to reduce overfitting. And then it depends from dataset to dataset, but one answer is regularization, reducing the size of network and increasing the dataset. But regularization itself is a big topic. Yes.
Okay. I guess there's one more question left. For this project, we should use CT scan images or X-ray images.
At the end of the day, you are going to convert it into numbers. So you can choose any. You can even choose some X-ray and some CT scan and train a model that understands both. But for a network, you have to convert it into some kind of a tensor, some kind of a matrix, And it doesn't matter whether initially it was a JPEG or a screenshot or an X-ray or an ultrasonic or a CT scan.
Okay, so I guess we are done with the questions. So before moving towards the quiz is just to sort of leave you guys on the lighter note after this heavy session. Uh, Shivang, if you have anything to share about our plans in future for the similar sessions as we discussed, and anything which you want to speak
Yes.
before concluding.
Yes. So our plan is to uh, deliver such sessions on different topics, and our plan is to do move into details of different aspects. We're planning to start from something small, want to give some kind of a hands-on experience on machine learning, where we can work with a team on some project where we meet on Saturdays and Sundays, and you and us discuss certain things, and then you implement it for the entire week, and we meet next week to discuss certain things. So we want to start from there, and if we find some people who are really interested, this is a plan that we are planning to, where we we mix and match some kind of programming skills first of all, where we talk something about competitive programming, not very detailed, so that people are really comfortable with programming. So initially we want to do some kind of a programming questions in Python, so that people who are new get a feel of it, understands, and it becomes easy for them to work on. Then we want to start with the concepts of machine learning and do some kind of case study, some kind of a problem where we take some data set and implement it, just not a one-sided discussion, but a project where we divide everybody into some teams, and you implement that project. We meet next week, and we keep on doing this practice again and again. And we touch different machine learning algorithms, starting from uh, uh, linear regressions to XGBoost and SVM, and we try to tackle some kind of Kaggle problems while doing it. We go algo by algo, implement some things, and then we get into neural networks. All the concepts that we discuss, each and every concept itself requires an hour of discussion. So if you talk about backpropagation itself can take 6 hours to talk. If you talk about gradient descent, it can take few hours to talk on gradient descent. You can implement gradient descent and backpropagation from scratch, and you can build your own neural network in C++ or any other thing, which itself is a great exercise to do and understand the concepts. If we talk about, there's some questions like image preprocessing. So image preprocessing itself has a lot of, or any kind of data preprocessing itself has a lot of nitty gritty into it. So we can discuss those things. So we take things component by component, go project by project, and this is a plan that we think can implement if we find a lot of people interested into it. And at the end of the day, one more thing, yeah, if there are some people who are really good into deep learning, we are always ready to hear from them. We are always looking for an opportunity, or we are always looking to give an opportunity and take some opportunity to work with people who are really good into these subjects. So that's another thing that is really cool, and really cool to reach out to you people and say that we want to develop a community where we want to promote AI, not only from the training perspective but also from the development perspective, so that more and more companies in the city uh, can uh, uh, can learn and can do great stuff into this thing. So we require a lot of people into this field. Uh, Companies have work, companies don't have people into this field, and we require good people to come ahead and get along these things and become really good in building AI powered software applications for the upcoming years. So that's it, Minal, and that's it from my side.
That's really great. So, like as Shivang said, like people who think they might really contribute to what we just mentioned. Definitely, you guys can reach out to any of us, be it from anyone from Tech Era community, or be it anyone from at DC Indore. We are always ready to help you guys. And yeah, thanks a lot again to Shivang for taking out his precious time and for sort of talking to us for an hour every day on a busy weekend as well. So yeah, thanks a lot. Now I would I'll share my screen for the Kahoot quiz just to sort of end the webinar on a lighter note. I hope you guys liked it yesterday as well. And I guess a lot of you are ready, and you might have opened the enter pin screen on Kahoot.it, right? So I'll just give me a second and I'll share the screen. Okay, guys, I hope you liked the quiz as well. I would request winners to reach out to us on any of our social media platforms to so that we can sort of highlight your that you won the quiz, and we might whatever action needs to be taken, we'll be taking that. Final announcements regarding the certificates and everything which you guys were asking that. So we are sharing the feedback forms link on your screen, so make sure you guys fill up the feedback form. If you need the feedback form for yesterday's session, just visit our YouTube channel, and you can we were showcasing it on the live stream yesterday, so you can have a look at there. For today's feedback form, you can have a look at your screens. Just make sure you fill up the feedback form so that we'll be able to know about how was the session, and also we'll be able to mail you back the resources which were used for today's session, be it the PPT or be it the notebooks which Shivang was using. So yeah, that's the two things. Also make sure you like, follow, share this particular video. Also follow us the YouTube channels of both the communities, and make sure you stay in touch with us on all our social media platforms, be it Facebook, Instagram, YouTube, wherever you want. You guys can reach out to us. We do organize similar webinars every weekend, be it on any technology. This week it was machine learning. There's a possibility next week we might do a webinar on open source. We have done a lot of webinars on Spark AR, and so many different things. We are not just limited to one particular thing. So yeah, that's all about the this webinar series. Once again, I would like to thanks Tekera community for this lovely collaboration which we did for this particular event. It was really nice working with you guys, and thanks a lot everyone for joining. I hope you liked the session. Let us know in the comment section as well as in the feedback form as well. Yeah, that's all from our side. Thanks a lot. Bye bye.